Hello everyone, this is lecture 3. Now we're going to do some applications of system of linear equations. So in the last two lectures, we talked about system of linear equations, and we can use either eliminations method or substitution method to obtain the solution of a linear system, or you can use Gauss-Jordan eliminations method, as well as you can use Python to provide you the reduced row echelon form of the augmented matrix to help you with the finding the solutions of the system. Right. So we learned about system of linear equations because there are many applications in real world problems that can be related to system of linear equations. And two of the applications I want to talk in this lecture is we can use system of linear equations to find these representations of polynomial functions from a set of data points. In the second application is we can use the system of equations to understand the flow in a network. This network can be fluid flow through a pipe, or it can be a traffic flow, right? And there's all the applications like electrical engineering flow, or the intensity or the current flow in electrical engineering. But that's for another topic. So again, the focus on this lecture is on two applications of system of linear equations. The first one is to fit a polynomial functions to a set of data points, and the second application is to solve system of linear equations to represent a network. All right, so let's talk about polynomial curve fitting. All right, now if you have endpoints on the plane, the xy plane, so the xy planes mean you have the x-axis and the y-axis, and so this is the x-axis and this is the y-axis, and they intersect at one point, and that point is the origins. Now if you have endpoints on the xy plane, x1 y1, x2 y2, x3 y3, so on and so forth up to xn or yn, you want to find a representations or a functions or a curve that best fit into this point given to you. And this whole process is called polynomial curve fitting. All right, so let me write down some information here. So what we're looking for in this case is to consider endpoints in the xy plane, and the points are, so the first point x1 y1, the second point x2 y2, the next point x3 y3, so on and so forth up to x sub n y sub n. Okay, and what we want to do is we want to find a polynomial, functions of degree n minus 1. All right, so why is n minus 1? Because you have endpoints, and in the polynomial that we're going to write down the formula, there will be n terms from a sub 0 up to a sub n minus 1. Altogether, you have n terms, so that's why we just do this up to a degree of n minus 1. All right, so what is polynomial functions? Some of you may recognize the terminology already, just in case you don't. So polynomial function is you have functions of multiple terms or multiple power functions in there. So you have p of x as the functions, which is the output in this case. Let's say you have one term, a sub 0, it's just a constant. Because it's just one term, so we call that monomial. All right, so let me quickly write it down. So this is monomial. All right. Now, if you add in another term, let's say in this case, you have a1x, right? So a1 times x raised to the first power. Now you have two terms in the functions. And with two terms, it means binomial because 2. So 2, so this is binomial, right? And if you play the same game and you add another term, in this case, going to be a2x squared. Now you have three terms in the functions. When you have three terms, it's going to be trinomial. But in general, what you can say is that, okay, this is the polynomial. That means multiple terms. So polynomial, because you have multiple terms of degree 2, because the highest power of x is 2, right? So that's why not only this is called the trinomial, but also polynomial of degree 2. In addition to that, you can add more term. And in this case, you're going to do this up to a sub n times x to the power n minus 1. So this is polynomial of degree. So polynomial of degree n minus 1. Okay. And how could you actually find the functions or representation of the functions through the endpoint in the XY plane? Is actually very simple, right? So what you can actually do is to just substitute all of this point into the polynomial, and then you obtain a system of linear equations. And from there, you can solve the solutions of a0, a1, a2, up to a sub n minus 1. Right, so at this point, what you can do is substitute endpoint, so endpoint into the polynomial functions b sub x to obtain a system of linear equations that can solve for the values of a0, a1, up to, let me do another letter here, so a2, and up to a sub n minus 1. All right, so basically just substitute what we have for this point into the polynomial functions. So here is the system. So let me do the first point. So you have a0 plus a1 x1 plus a2 x1 squared, so on and so forth, up to a sub n minus 1 times x1 to the power n minus 1. And you that equal to the right hand side, right, equal to the output. The output in this case, the y value. And this is the first point. So the y value is y1. So 1 point, 1 equations. Now you have n points, you're going to do that n times, right? So you have the next point to be a0 plus a1 times x2 plus a2 times x2 squared, so on and so forth, up to a sub n minus 1 times x2 raised to the power n minus 1 and equal to y2. Right. So I'm not going to write everything down up to n case, right? So I'm just going to skip all the equations and just write the last case or the last equations. That is a sub 0 plus a1 x sub n plus a2 x sub n square plus a sub n minus 1 times x sub n raised to the power n minus 1 and equal to y sub n. Right, so you have n points, you have the polynomials of degree n minus 1. And to find the value of a0, a1, a2 up to a sub n minus 1, what you do is you substitute endpoints into the polynomial functions. and you obtain a linear system of linear equations. And from there, you can solve for the value of A0, A1, A2, so on and so forth. All right, so that's the theoretical part of the polynomial curve fitting. So let's go through a couple of examples in this lecture related to polynomial curve fitting. So the first example is the polynomial of degree 2, right? Because the highest degree is the highest power of x is 2. So let me quickly note that this is polynomial of degree 2. Right. So this functions, or the graph of the function, passes through 3 points, 1, 4, 2, 0, and 3, 12. So what we do is we're going to substitute this point into the polynomial functions to obtain a system of linear equations. All right, so the points are 1, 4, 2, 0, and 3, 12. Right. So P1, right, because for this point, the first component is 1, so x equal to 1. P1 is A0 plus A1 times 1 plus A2 times 1 square equal to 4. Now for the second point, you have B2, which is A0 plus A1 times 2 plus A2 times 2 square equal to the output, which is 0 in this case. And for A3, you get, sorry, P of 3, you have A0 plus A1 times 3 plus A2 times 3 square, and this is equal to 12. Okay, so that's the process. Given 3 points, and you want to determine the value of A0, A1, and A2 for the polynomial of degree 2, you set this up, and you obtain a system of linear equations of 3 variables, A0, A1, and A2, and 3 equations, right? So the system becomes so you get A0 plus A1 plus A2 equal to 4. Then A0 plus 2A1 plus 4A2 equal to 0. Then A0 plus 3A1 plus 9A2 is equal to 12. Again, you have a system of linear equations. Again, now you have multiple ways to solve the solutions of the system of linear equations. So this is simple enough that you can just use substitution method, eliminations method, and or Gauss-Jordan eliminations method by hand, right? But to save time, we can actually input all the information into Python to give us the reduced row echelon form to help us solve for the solutions of the system, right? So what I'm going to do is I'm going to write down the augmented matrix, and I'm going to jump into Python to actually calculate the value of A0, A1, or to find the reduced row echelon form of the augmented matrix. So the augmented matrix is, so you get one side is the coefficients matrix 1, 1, 1, and on the other side is the constant matrix. So this 1, 2, 4, 0, and the last row is 1, 3, 9, 12. And I'm gonna say that using Python in this case, and I'm going to obtain the reduced row echelon form. So let me jump into Python now. Okay, so we in Python coding or Jupyter coding environment, and I'm going to change the file, the name of the notebook to lecture 3. And I have that. All right, so to get to help me with the input of the augmented matrix, you get to import the numpy and also the sympy. So numpy is the numerical libraries, and sympy is the symbolic library. So we do from numpy import star, and from sympy import star as well. Now you want to create a matrix, right? So in our example, this is the matrix of 3 rows and 4 columns. So create a 3 by 4 matrix of the form, and I call this matrix A. This is an array. Right, so the first row consists of the entry 1, 1, 1, 4. The second row, we go to the next line, it's going to be 1, 2, 4, 0. And the last row is going to be 1, 3, 9, and 12. And let's print this out. So just to make sure this is working. So print out value of A. All right, so it's working. So this is the augmented matrix. All right, so print out the augmented matrix. Okay, so now what you want to do, of course, is to obtain the reduced row echelon form, and that can be done using the sympy, right? So from the last lecture, what we did is we do matrix A and use reduce row echelon form, open and close parenthesis, but you just need to obtain the first entry of the output, right? And I'm going to comment out the print8. So that, now I hit Shift Enter, and this give me the augmented matrix or into the reduced row echelon form. Okay, so that's just good for us. Now let's go back to the notes. All right, so from Python, we obtained the reduced row echelon form of the augmented matrix of the form 1, 0, 0, and then 24, and 0, 1, 0, negative 28, and 0, 0, 1, and this is positive 8. Okay, so that means A0 is equal to 24, A1 is equal to negative 28, and A2 is equal to A. Right. Therefore, the polynomial functions is P of x is equal to 24 minus 28x plus ax squared. Right. And again, this is polynomial functions of degree 2. And there's another name for that. This is called the quadratic functions. And the graph of a quadratic functions is a parabola. And you can see that the parabola fit into these 3 points, right? So which is good. So that's it for this problem, for this example. Let's move on to the next example. Now, in the next example, you have 5 points. So therefore, you need to use a polynomial functions of degree 4 to fit into 5 points, right? So again, when you have n points, the polynomial functions of degree n minus 1 need to be used. In the last example, you have 3 points. right? So therefore, you need a polynomial of degree 2 to fit into this 3 points. And again, in this case, you have 5 points. You need a polynomial functions of degree 4. All right, so let's set that up. So we use a polynomial functions of degree 4 to fit the given 5 points. Right. So the function is of the form. Right. So you have P of x is equal to a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the fourth. Now, we need to obtain the system of linear equations to solve for a0, a1, a2, a3, and a4. Right, to do so, you just substitute this 5 point into the functions. Then you have, so a0 plus a1 times -2 plus a2 times -2 square plus a3 times -2 cube plus a4 times -2 to the fourth equal to the output, which is 3 in this case. All right, so that's for the first equation. And you have 5 points. That means you need to have 5 equations. All right, so the next equation is going to be for the point -1, 5. So for this next one, you have a0 plus a1 times -1 plus a2 times -1 square plus a3 times -1 cube and equal to +5. Okay. The third equations will give you, the third equation is for 0, 1. This is going to give you a0 plus a1 times 0 plus a2 times 0 square, and so on and so forth. And the output is equal to 1. All right. The fourth equation is a0 plus a1 times 1 plus a2 times 1 square plus a3 times 1 cube plus a4 times 1 to the fourth, and that is equal to 4. The last equation, a0 plus a1 times 2 plus a2 times 2 square plus a3 times 2 cube plus a4 times 2 to the fourth equal to the output, which is 10 in this case. All right. So now you can quickly calculate the value of -2 squared, -2 cubed, so on and so forth to so you don't have to keep writing the power anymore. Okay, so the system becomes that you have a0 minus 2a1 plus 4a2 minus 8a3 plus 16a4 equal to 3. So that is the first equations. Right. The second equation is a0 minus a1 plus a2 minus a3 plus a4 equal to 5. The third equation is just a0 equal to 1. The fourth equation is a0 plus a1 plus a2 plus a3 plus a4, and it is equal to 4. And the fifth equation is a0 plus 2a1 plus 4a2 plus 8a3 plus 16a4 this equal to 10. All right. So now I'm going to input the augmented matrix of this particular system into Python, so I don't have to do any calculations by hand, because the system of 5 unknowns in 5 equation, which is a little bit hectic to do, difficult to do. Okay. All right. So this is example 2. So let me quickly comment that. So example 2. And the one above that is example 1. So in this example 2, from the node, what we want to do is to create a, so you have how many, so you have 5 equations, so that is 5 rows by 6 matrix of the form. I am going to call this matrix B. And I need an array, right? So the first row consists of the values of 1, -2, 4, -8, 16, 3. The second row is 1, -1, 1, -1, 1, and 5. The third row is just 1, 0, 0, 0, 0, and 1. The fourth equation, so the fourth row is 1, 1, so a bunch of 1 here. And the last entry is 4. And the last row is 1, 2, 4, 8, 16, comma, 10. Right, so let's print out this matrix, make sure it's working. So I'm missing something here. So I forgot to close this. Okay, so there's no open bracket, and I need to close bracket, so it should work now. So this is the matrix that we have. Now we need to run the reduce row echelon form command. Reduce row echelon form, and just choose the first entry of the output. All right, so this is the reduced row echelon form, and you can see that A0 is equal to 1, A1 is equal to -5/4, A3 is 101/24, A4 is A3 is 3/4, and A4 is -17/24. All right, so let me go back to the notes and we're going to write out the representations of the polynomial functions. All right, so I get that from Python. We obtain A0 equal to 1. A1 is equal to -5/4. A2 is equal to 101/24. A3 is equal to 3/4, and A4 is equal to -17/24. Right? Therefore, the polynomial function is of the form P of x equal to 1 minus 5/4x plus 101/24x squared plus 3/4x cubed minus 17/24x to the fourth. And that is the functions in the graph. The functions is given here that fit into the given 5 points. All right, so that's a good 2 example for the polynomial curve fitting. In the next example, we also is going to use the polynomial curve fitting to come up with a formula for some real world data. Okay, and from that particular polynomial functions that you obtain, you can actually use it to predict the informations in the future. Okay, so in this case, what we do is we want to look into the US Census population data. And this is the real data that I got from the US Census website. And the population, including the year of 2000, 2010, and 2020. And the populations in the US is 282 million people. In 2000, 2010 is 309 million people. And in 2020 is 332 million people. All right, so the first part is because you have a set of 3 data points, and we're going to use a quadratic polynomial functions or polynomial functions of degree 2 to fit this 3-point data. And then after part A, you have functions or the polynomial of degree 2 functions. We're going to use that to predict the population in year 2030 and 2040. Okay, so before doing the or form the linear system of linear equations, what I'm going to do instead of using the year 2000, 2010, 2020, I'm going to simplify my calculations a little bit by letting the entry 2000 as t equal to 0. The entry of 2010 is t equal to 10. And the entry of 2020 is t equal to 20. Okay, and later on when we do the year of 2030, this is the value of t equal to 30, and the year 2040, this is t equal to 40, right? But that's for part B. Now in part A, right, we use polynomial functions of degree 2 to fit the data, right? The data is 0 to 82. That's the first point. The second point is 10, 309. And the third point is 20, 332. All right. So the polynomial function is of the form, right? So P, the function is, so P of x equal to a0 plus a1x plus a2x squared. And you're going to substitute this into the system. This point into the functions to obtain the system, right? So you have P0 is equal to a0 plus a1 times 0 plus a2 times 0 squared equal to 282. So that's the first equation. The second equation is a0 plus a1 times 10 plus a2 times 10 squared equal to 309. And when P of 20, you have a0 plus a1 times 20 plus a2 times 20 squared equal to 332. Right, so that's the system of 3 unknowns and 3 linear equations. Okay, so I'm going to go into Python one more time. To obtain to calculate the reduced row echelon form of the augmented matrix of this system, so I don't have to do it by hand. Okay, so I'm gonna use Python to find the value of a0, a1, a2. All right, so I'm gonna do some comments here. So this example 3. What we want to do is we create the A3 by 4 matrix of the form, right? So I call this matrix B, right? And the matrix B consists of 3 rows and 4 columns. The first row including the entry of 1, 0, 0, and 2A2. The second row consists of the entries of 1, 10, 100, and 309. And the last row consists of the entry of 120 and 400 and 332. So let's print out the value of C, see if it works. So it works. And comment this out, and we're going to do matrix C dot RREF and just choose the first entry of the output. Okay, so this is what we're going to see. All right, so A0 is equal to 282, A1 is equal to 29 over 10, and A2 is equal to negative 1 over 50. So let me go back to the node now. So from Python, we get that A0 is equal to 282, A1 is equal to 29 over 10, and A2 is equal to negative 1 over 50. Right. So I'm apologize for this raw setup here. Eventually we're gonna fill out some information, but let me continue writing in this space right here. Okay, I'm gonna delete it later to use the space for the network analysis. Okay, so the polynomial functions is that P of X equal to 2A2 plus 29 over 10 X minus 1 over 50 X squared. Okay, so that is part A. You come up with a polynomial functions of degree 2. Now we're going to use this to obtain the value of the future data. Okay, so what we do is we want to, so part B, we want to calculate the populations in the year of 2030. So that is T or X equal to 30. All right, so P of 30 is 2A2 plus 29 over 10 times 30 minus 1 over 50 times 30 square. Okay. And this is going to be equal to 351. So this is millions of people. Right. And we're going to do the same calculations, but for the case of X equal to 40. So P of 40 is equal to 2A2 plus 29 over 10 times 40 minus 1 over 50 times 40 squared. Right. So this is quick calculations. So let me do quick calculations here. And this is going to give you 366. So this is millions of people. Okay, so in this case, in this example, what we did is we use a polynomial curve fitting to find a functions that fit into these three particular real life points, data point, and we use the functions to provide a prediction for the populations in the future, which is, I think, is a very cool technique to know. All right, so that's it for the curve fitting, polynomial curve fitting. Now the next application is for network analysis. Okay. All right, so the next application is for network analysis. So networks analysis, So the network composed of branches and junctions are used as model in such field as economics, traffic flow, and electrical engineering. So let me write the information down for us. So networks composed of branches and junctions are used as models in such fields as economics, traffic flow, and electrical engineering. Okay, so it's going to be very simple, right? So this is one very simple network where you have this are called branches and this is the junctions, right? So let's see in terms of traffic flow, you have 25 cars come into these junctions and it's going to break or diverge into two different directions. That means it's maybe one car is going to this direction and 24 cars in this directions, or two cars in this directions, or and 23 cars in this directions. In either cases or any cases for that matter, what you need to know is that whatever coming in has to be equal to the sum of the outflow. Okay, so that is 25 coming in equal to x1 plus x2, right? Or you can also write this as x1 plus x2 equal to 25. So that is how you set up the system for this particular network, or the equation for this particular network. Now, moving on to the example, then so you have more complicated setup at this point. Right now, you have 5 junctions and multiple branches. Okay, so how would you find the information of x1, x2, x3, x4, and x5, given the informations that, let's say, going from junctions 2 into junction 1, you have 20 cars going to that particular directions. There are 10 cars going from 3 to 4 and 10 cars, let's say, going from 3 to 5. Now you want to know how many cars going from 1 to 4, how many cars going from 1 to 3, so on and so forth, right? So I'm going to analyze each junctions. At each junctions, I'm going to have one equation. Now I have 5 junctions. That means I have 5 equations with 5 unknowns to help me with system of linear equation. All right. So for junction 1, right? So there are 20 coming in and x1 and x2 coming out. So you have x1 plus x2 equal to 20. So that in junction 1. Right, so in junctions 2, you get x3, right? So junction 2, x4 is coming in, x3 and 20 coming out. What you can do is, so coming in x4 equal to x3 plus 20, or you can rewrite the system as negative x3 plus x4 equal to 20. So let me know, this is the first equation I'm going to use. This is the second equation I'm going to use. All right. Now in junctions 3, so junction 3 here, there are multiple branches going in and out of these junctions. So x2, x3 coming in, 10, 10 going out. So coming in x2 plus x3 equal to 10 plus 10 equal to 20. So this is the third equations. junction 4. So in these junctions, you get x1 and 10 coming in and x5 going out. So x1 plus 10 equal to x5, or x1 minus x5 equal to negative 10. This is the fourth equations I'm going to use. And for the last junctions, or junction 5, you get 10 and x5 going in, and x4 going out. So x5 plus 10 equal to x4, or negative x4 plus x5 equal to negative 10. And that is the fifth equations. Okay, so we can write down from this analysis, we can write down the system of linear equations. Right, so the system of linear equations is, so what do I got? So we got x1 plus x2 equal to 20. That's the first equation. Then x3, sorry, second equation, negative x3 plus x4 equal to 20 as well. Move this over here. So junction 3, or this third equation, is x2 plus x3 equal 20. Then x1 minus x5 equal to negative 10. And negative x4 plus x5 equal to negative 10 as well. All right, so this is the system of 5 equations in 5 unknowns. And we can come up with the augmented matrix of the system. Right. So this is the augmented matrix of the form 1, 1, 0, 0, 0, 20, 0, 0, 1, negative 1, 0, negative 20, 0, 1, 1, 0, 0, 20, 1, 0, 0, 0, negative 1, negative 10. And the last equations, let me erase this a little bit. The last equation is 0, 0, 0, 1. Sorry, negative 1 and 1. And this is positive 10. So I make some mistake here. This is positive 20. And this is negative 1 plus 1. Okay. So now I'm going to go to Python and set up this particular matrix to help me with the reduced row echelon form to obtain the value of x1, x2, x3, x4, and x5. Okay, so we get example 4, and we're going to create a, so there are 5 rows and 6 column matrix of the form, and we call this D, matrix D, need an array. So the first row consists of the entry 1, 1, 0, 0, 0, 20. The second row consists of 0, 0, negative 1, 1, 0, and positive 20. The third row is 0, 1, 1, 0, 0, comma 20. The fourth one is 1, 0, 0, 0, negative 1, comma negative 10. So the last one should be 0, comma 0, -1, +1, and -10. So I make a little bit mistake here in the note, and we'll go back and fix that later. So print out this particular matrix, so it works. So comment this out, and we can use reduce row echelon command from Python to help with our calculations. And we see that there's some possibility here, right? Okay, so the network going to give you that the last row is going to be a bunch of zeros. So we only have 4 equations with 5 unknowns. And from the theorem that we have in the last lecture, that if the number of equations less than the number of variables of unknown, right, we're going to have infinitely many solutions, right? So there are infinitely many solutions for this particular case. All right, so I'm gonna take this information, go back to the note to help me. Now we're going to write down the solution set of the infinitely many solutions case. So one thing I want to quickly mention is that I forgot to put in the -10 in this case. Right, so this should be a -10 to stay consistent with the system we wrote down here and also the code that we just did. All right, so let me erase this augmented matrix so that we can just write down the reduced row echelon form. So it's going to be sorry, we're just going to write down the system, right? So Python, from Python, we obtain the following system. That x1 minus x5 equal to -10. X2 plus x5 equal to 30. X3 minus x5 equal to -10. And x4 minus x5 equal to +10. So in this case, we can see that we can solve for x1, x2, x3, and x4 in terms of x5. And we say that x5 is a free variable in this case, right? So it implies that x1 is equal to x5 minus 10. X2 is equal to -x5 plus 30. X3 is equal to x5 minus 10, and x4 is equal to x5 plus 10. And this is going to be equal to t minus 10 if you let x5 equal to t, for t is any number for that matter, equal to -t plus 30, t minus 10, and t plus 10. So even though we say that in the theoretical sense, if we say that t is equal to 0, you have x1 to be -10, it doesn't really make any sense in terms of traffic flow. But for a theoretical sense, it still work, might still work. In the case that we're not sure what kind of network flow is going to be. It can be electrical flow, it can have negative implications. Okay. All right, so again, in this case, t is any real numbers, right? For now. Right, so for now, so it depends on the particular network that we're working with. we need more information to actually restrict the value of t. But in this case, we can just choose t equal to any real numbers. Okay. So the next example is more realistic because you want to know about the flow of traffic through a network of telephone towers. So this is the schematic of the telephone towers, the network of the telephone towers. What we're going to do is first set up a system of linear equations of the traffic flow. The second one is to solve the system for x1 up to x5. And then we can use, we're going to find the traffic flow when x2 is equal to 20 and x3 equal to 5, and as well as in the fourth part, we're going to find the traffic flow when x2 is equal to 15 and x3 is equal to 0. Okay, so let's first set up this system of linear equations. Well, now you have 4 junctions. We're going to do the analysis for the 4 junctions. So junction capital A, right? So you have 30 going in and x1 and x2 going out. So that is 30 equal to x1 plus x2, or you do x1 plus x2 equal to 30. And that is the first equation that I'm going to use. For junctions B, we have that x1, x3 coming in, x4 and 15 going out. So x1 plus x3 equal to x4 minus plus 15. Therefore, you have x1 plus x3 minus x4 equal to positive 15. So that's the second equation. The third equation is coming from junctions capital Y. That is, at these junctions, you have just 20 and x2 coming in, x3 and x5 going out. So you get x2 plus 20 equal to x3 plus x5, or x2 minus x3 minus x5 equal to negative 20. And for junctions Z, you have x5 and x4 coming in and x3 coming out. 35 coming out. So x4 plus x5 equal to 35. And this is so this is the third equation. This is the fourth equations. And we obtain the system. The system is of the form that x1 plus x2 equal to 30. X1 plus x3 minus x4 equal to 15. And x2, let me move this out of the way a little bit. So x2 minus x3 minus x5 equal to negative 20. And x4 plus x5 equal to 35. So there are 1, 2, 3, 4 equations, but 5 unknowns. So we know that there's going to be infinitely many solutions for the case of the system. Right. And then from here, what we can do is you can form the augmented matrix and use Python to help with the reduce row echelon form. So I'm going to skip that particular part because we already did that for the last four example. So I'm just going to write down the solutions here. So the reduce row echelon form of the augmented matrix of the system is of the form 1, 1, 0, 0, 0, 30, 0, 1, negative 1, 1, 0, 15, 0, 0, 0, 1, 1, 35, and the last row is the bunch of 0. Again, we have a system of starting with 4 equations and 5 unknown. Now we obtain the system of just 3 equations and 5 unknowns. Right? So this is the augmented matrix of the system. You have x1 plus x2 equal to 30. X2 minus x3 plus x4 equal to 15. And x4 plus x5 equal to 35. All right. So now I'm going to solve x1 in terms of x2. And x3 is in terms of x2 and x4. Right. So negative x3 equal to negative x2 minus x4 plus 15. And x5 is also in terms of x4. So negative x4 plus 35, or the system is now equal to x1 equal to negative x2 plus 30, x3 equal to x2 plus x4 minus 15, and x5 equal to negative x4 plus 35. Okay, now for this system, you have 2 free variables. In the free variables, which is x2 and x4, right? You can let x2 equal to t1 and x4 is equal to t2, right? So let x2 equal to t1 and x4 equal to t2. We got that. X1 is equal to negative t1 plus 30. X2 equal to t1. X3 is equal to t1 plus t2 minus 15. X4 is equal to t2. And the last part, x5 is equal to negative t2 plus 35. Okay, so that is the solutions of the system, and the system again has infinitely many solutions, and that going to be a little bit tricky to analyze if you don't know more about the information given to you. All right. So to make the analysis more realistic, we need to come up with a constraint for T1 and T2. In this particular case, you can say that T1 can be has to be less than or equal to 30. Otherwise, if you have a negative number, it's not going to work. And T2 from here is going to be less than or equal to 35. As well as in this case, the sum of T1 and T2 has to be greater than or equal to 15. So that are some constraints that you need to input to make the analysis more realistic. In addition to this, because the system has infinitely many solutions, this is just one way for you to choose the free variables. There's another way to obtain the free variable, right? So based on the problem given to us in this case in part C and D, that they want to know what's the value of the traffic flow when x2 and x3 equal to 20 and 5 respectively. Okay, so what we do is that we're going to come up with another setup for the free variable. In this case, we're going to choose x2 and x3 as free variables. instead of x2 and x4 in this case. All right, so part C. So what we do is we're going to solve x1 in term of x2. You have x1 equal to negative x2 plus 30. And x4 can be solved in term of x2 and x3. So negative x2 plus x3 plus 15. And x5 equal to negative x4 plus 35. But we have decided that x2 and x3 are free variables. So we're going to write x5 in term of x2 and x3 as well. So that is negative of negative x2 plus x3 plus 15 plus 35. So this is going to give us x2 minus x3 plus 20. All right. So in this part C, you want to know the traffic flow when x2 is equal to 20 and x3 is equal to 5. So when x2 is equal to 20 and x3 is equal to 5, then x1 is equal to negative 20 plus 30 equal to 10. Of course, x2 is equal to 20 and x3 is equal to 5. Then we can do x4 to be negative 20 plus 5 plus 15 is equal to 0, and x5 is going to be 20 minus 5 plus 20 is equal to 35. Okay. So next in part D, right? So the same setup for the free variable. So let me quickly note again that x2, x3 are free variables. Okay, and so this case you have x2 to be equal to so in part D, x2 is equal to 15 and x3 is equal to 0. Right, so therefore x1 is equal to negative 15 plus 30 equal to 15. x2 is equal to 15, x3 equal to 0, x4 is equal to negative 15 plus 0 plus 15 again. This gives me 0. And x5 is going to be 15 minus 0 plus 20, and this is equal to 35. So that's it for this lecture. So in this lecture, we look at two applications for system of linear equations. The first one is to use polynomial functions to fit some data points, or another name for that is polynomial curve fitting. And the second application is to use system of linear equations to solve for some network flow or the flow of network. All right, so that's it for me. Please let me know if you have any questions.